In a number of previous videos, I used this box or one like it to display current waveforms from things like light bulbs with electronic power supplies on the oscilloscope. And a number of people expressed an interest as to what was in this box, and one viewer in particular, Mike Gates, named the box the Magic Box. And, well, this video's about what's inside my magic box. So here's the box we used with an oscilloscope in the power factor and other videos to look at the currents flowing into various electronic power supplies, such as for common electronic light bulbs, the LED variety or fluorescent ones or what have you. And, well, let's open it and see what's inside. And if we look inside, perhaps the most notable components are these two big giant resistors. They're both rated at 50 watts, and they're attached to this switch, and the switch allows us to select the sensitivity. So in one setting, if we hook a oscilloscope or voltmeter between the neutral and the current output, we get 1 volt for every amp of current that's flowing through the system. And if we have it in the other settings, well, we need to multiply the voltage by 10 to get the amount of current that's flowing. So that's very convenient. I did make another box that is more sensitive, so it operates in the milliamp range by using larger valued resistance, but the principle is the same. We also have, if we look inside here, a voltage divider, and that voltage divider is used to give a voltage here that is 1% of the applied AC voltage to the plug. And so that means for 100 volts being seen on this receptacle, we should get 1 volt going to our voltmeter or oscilloscope or both. And that's basically the way you would use this thing. I did add 2 other devices to it, one of which was a lamp that comes on when there is 120 volts power applied. Turned out not to be very useful because it's not bright enough to normally see very easily in a well-lit room. And another lamp in here that tells me if, when we've plugged this system into the wall plug is wired so that the live and neutral are reversed, and that might be dangerous with this sort of setup. So that's the idea, and what we should do is take a look at this box from a schematic standpoint, and I can tell you a little bit about how to size these resistors. So maybe we'll start by drawing a simple schematic. Here's the receptacle on the box. There's its ground. We'll just draw the ground like that. And over here is the AC power plug. We'll give it 2 prongs, a live and a neutral, and it also has a ground in the middle, and we'll just indicate that it's connected to this ground as well as the metal case of our box. And similarly, we'll mark this live and this neutral over here so we can keep track of things. And what we'll do is connect the live from our plug, perhaps through a fuse if we're so inclined. Not a bad thing to do for reasons we'll see when we size the resistor, over here to the live part of the receptacle. And what we'll also do is get our neutral from the wall outlet over here and bring it down here, but unlike what we might normally do, we'll take the output of our receptacle on the box and feed it through two resistors, and these are those big giant 50-watt resistors that I showed you in the box itself. And one of these resistors is 1 ohm and the other is 1/10 of an ohm. So we'll make this one up here 1 ohm, and we'll make this one 1/10 of an ohm. And to switch the sensitivity of the box, we'll put a switch over here like this. So this is our sensitivity switch that essentially, when it's closed, shorts out the 1 ohm resistor. So when it's closed, we have a 1/10 of an ohm resistor in here. And oh yes, what we need to do is take a wire from this point in our circuit, and that will be going to our banana plug jack labeled current I. And the other thing we'll do is we will use our neutral over here, and we'll connect it to another banana plug jack, and we'll label it G for ground, or earth in some other parts of the world. What happens if we plug in, say, something like a 100-watt incandescent light bulb, and we'll say it draws 1 amp of current? Well, that 1 amp comes through here, and if this is closed, it'll go through this resistor, and the voltage we'll see across here, in other words, from here to here, will be 1 amp times 1/10 of an ohm, or 1/10 of a volt. And similarly, if we were to put a heater maybe attached to this and draw 10 amps, now 10 amps flowing through this switch, it's closed, and this 1/10 of an ohm resistor will produce 1 volt between here and here, or between here and here. So we'll see 1 volt between our current sense output and ground. Now, if we open this switch, well, now we have these two resistors in series, so together we would end up with 1.1 ohms. And, well, if we had 1 volt flowing through the system, we would now get 1.1 volts at our current sense terminal over here. Now, you might say it would be a lot nicer if we had 1 volt corresponding to 1 amp as opposed to 1.1 volts corresponding to 1 amp through the system. Well, we could certainly do that, and if we wanted to do that, we would need to make this resistor not 1 ohm, but 0.9 of an ohm. So when added to this resistor, we get a total of 1 ohm of the two of them in series. Well, how could we do that? Now, here's where we separate practicality from theory. High power resistors are not cheap, and they usually come in certain sizes, often in sizes like 1/10 of an ohm or 1 ohm, less often in sizes like 0.9 of an ohm. So how could we make this into a 0.9 of an ohm resistor? Well, we can get pretty close by putting another resistor in parallel like this. And what would that resistor be? Well, the closest easy value would be 10 ohms. And so we put 10 ohms in parallel with 1 ohm. What do we get? Well, 10 ohms in parallel with 1 ohm gives us, and I just calculated it, 0.91 ohms. So, is this good enough? Well, that 0.01 is about 1% away from the 0.9 ohm value that we would like. That's probably good enough because most of these resistors are probably in the 1% range. We could put a little bit more in parallel here to refine this value down just a bit. And indeed, the next value we could put in here is not 10 ohms, but 100 ohms. So we could have 100 ohms in parallel with 10 ohms in parallel with 1 ohm, and that would get us even closer. And indeed, we could add more and more resistors as close as we want to get, but again, since these power resistors are typically 1%, at least if they're inexpensive, well, it doesn't make much sense to do much better than perhaps this. So that's what I could have done in my setup. In my setup, I didn't bother with this resistor. I decided, well, I'm really less concerned about measuring a precise value that I can easily translate to volts, and more concerned about just keeping everything simple. So there you have it. Now, I did mention that these were 50-watt resistors. And you may remember that there is a formula that looks something like this. Power equals I squared R, where R is the value of a resistor, I is the current flowing through it, and that's the power being dissipated. Well, we can run that backwards, and if we rearrange things a bit, we can get the current equals the square root of the power divided by the resistance. And what does that mean? If we have, in the case of our 1 ohm resistor over here, and we put a power of 50 watts over here, so this P is 50, this R is 1 ohm, what do we get? We get a maximum current of 7 amps. So if we have 7 amps flowing through this circuit in this 1 ohm resistor over here, well, we'll be getting 50 watts of power being dissipated. So what that really means is this circuit better never be used for more than 7 amps, because if it is, it'll overheat this resistor. And you might remember these resistors are attached to the side of the metal box that I used, which helps them dissipate heat, and indeed they generally need that to dissipate their full rated 50 watts. So it might be nice to make this fuse over here something close to 7 amps to prevent this resistor from burning up. Now what about this resistor? So if we had a 1/10 of an ohm and 50 watts, what do we get? Well, we can crank through the same equation over here, and this will allow us to pass 22 amps through the system. Indeed, more than this plug or this receptacle is actually rated for. So you can sort of see that I didn't really need as big a 0.1 ohm resistor as the 1 ohm resistor if I'm going to put a 7 amp fuse in here and only allow 7 amps to be passing through the system. But the reason I did choose both of these at 50 watts is for a very simple engineering principle. They were cheap. So that's what I did, and it works fine. All right. Well, that's very nice. The only other thing that this is missing is a voltage sense, because we'd really prefer not to have our oscilloscope attached to 120 volts as we would normally see on this over here. So what we'll do is we'll take a wire over here, we will use a voltage divider like this, and the output from the voltage divider to another banana plug, that's our voltage. And what we would like to do is indeed have this voltage here either 1/10, or in the case of my box, 1/100th of the voltage going in. And the way to do it would be to put a 1k ohm resistor here, and we want to keep this resistor reasonably low so that we don't get too much stray noise messing up our measurements. And at the same time, we want to keep it reasonably high so that we're not drawing too much current through this voltage divider, which is really doing no useful work other than giving us a voltage. So what that means is over here we need a 99k ohm resistor, and if we put that through the voltage divider rule, well, V out, which would be this point over here, is equal to V in times, and this is V in up here, by the way, times R1 over R1 plus R2. And R1 is this over here, so 1k, and R1 plus R2 is the sum of these two, 1k plus 99k, and if we put it all together we get 1k over 100k equals, and there should be of course V-ins along here, V-ins along here, or 1 over 100th of the voltage at V-in. Now, we should also consider the power of these resistors, because we don't want to accidentally burn them up. In the old days it wasn't a problem because usually resistors are pretty big. These days they make them tiny, like 1/10 of a watt or so. Well, what we can do is we can use the voltage version of this, and the voltage version of this is power equals the voltage squared over R, and well, it's going to be this resistor that is the problem. So if we expanded this a bit and we used a voltage of 120 volts and we used a resistance of 99k, well, what type of power dissipation would we be getting? Voltage squared, so 120 squared divided by 99k, that'll give us 0.15 watts. So what that means is this resistor should be bigger than 0.15 watts. So it would be nice if it was something like 1/4 of a watt, which would be a typical size. This resistor can be way smaller than that. It can be about 1% the size of this one. Well, you don't get tiny resistors like that, so what we'll simply do is also use something like a 1/4 watt resistor for it over here. If we decided to use smaller resistors, or if we decided we wanted this to be 1/10 of the voltage input, so this was only 9k, well, we would have to redo our power calculation over here, and we'd see that indeed we need a higher wattage resistor at that position. So that's what's inside our box. I did mention that I did have an indicator lamp to warn me if the live and neutral were reversed, and so what I actually did was I had an indicator lamp attached like this between the neutral and the ground. And so what the idea would be is if live happened to be attached to what I thought was neutral, well, this lamp would hopefully light up and warn me. Now, why did I do that? And that's because I am depending for safety on the fact that we use polarized plugs in North America. And polarized plugs can take various forms. If they're just two prongs, one of the prongs is wider than the other. In a three-prong plug, like this one and the one we're using here, well, it's the position of the two prongs relative to the ground that differentiates between live and neutral. So I'm depending on the fact that somebody wired the electrical outlet with receptacles like that properly, and what I think is live is indeed live, and it may not be. And that could be very dangerous. That's why I have this warning here. I would still always check the outlet with an outlet checker just to confirm that live is live and neutral is neutral, and for that matter, ground is ground when I'm using a device like this. Now, why might you ask, would I use a device like this that does depend for its safety on the outlet being wired correctly? Well, in North America, we indeed do that for a number of electrical devices, and it is a fairly well regulated region of the world, so we can generally trust that, although somebody might be having a bad day, some DIYer comes in, rewires their own outlet, and that's why, as I said, I would always check the outlet I'm using this box with a wiring tester to make sure that the outlet is indeed wired properly. If it wasn't, we could end up with the neutral here, what we think is neutral now live. We plug the ground or neutral pin of our oscilloscope into this, and suddenly the chassis of our oscilloscope is up at 120 volts. Not a good thing. So that's what we do in North America. Now, in the rest of the world, you might have problems because not all places have polarized plugs. Germany is a great example. And for that, we would need a version of this box that indeed keeps us somehow separated from the potential problem of live and neutral being reversed, because again, the plugs don't help us. And that will be the subject of the next video. Well, that's what's inside my magic box, and I should point out that one of the features of a box like this using a shunt resistor to measure the current or display the current on an oscilloscope is the fact that the shunt resistor allows us to easily see frequency components well up into the kilohertz, if not megahertz region. And that's really important with those spiky waveforms from things like electronic power supplies that easily have harmonics up into those regions. Now, the downside of a box like this is it does rely on a polarized power plug to keep what we think is the neutral connector indeed at neutral as opposed to being at live or 120 volts. So a box like this would not work well in various countries that have non-polarized plugs, typically the 240 volt countries. And for those situations, what we really should have is a box that uses transformers for both the current and voltage outputs to keep the person using it safe. And that's the subject of the next video. So I hope you found this interesting and useful. If you did find it interesting, please like or subscribe. And if you have questions or comments, please put them below. It's always fun to see what goes on in the comments, and see you next time.